Hello everyone, and welcome to Time to Fly Drone and AI Tutorials. This is part 2 of my KMeans mini-series, and if you have not yet seen part 1, where I give an overview of KMeans and how to use it with Scikit-Learn, definitely check that out. In this video, I will be going over how to implement our very own KMeans algorithm. Now, let's get started with KMeans explained. Now let's get started in implementing our KMeans algorithm. Once again, I'm running this video through a Jupyter notebook, and if you want to download this notebook, I've added a link to my GitHub in the description, so go ahead and download that and follow along if you want to. First, what we're going to do is load some imports, and now let's go over some of the functions we'll need to implement for our KMeans algorithm. So, as in the previous video where I went over KMeans, we're basically just going to be stepping through those exact same steps and now just writing up the code. So the first thing we need to do is a compute distance function, where we calculate the distance from every data point to the center of each of these groups. And we use this to assign each data point to its group. We'll also be computing the loss of our overall data set in order to determine how well our cluster centers represent our dataset. For the initialization process, we'll initialize our centroids by selecting random data points for our cluster centers. We'll update our centroid assignment by assigning each data point to the cluster it is closest to. We'll then update our centroids according to just averaging the features of all of the data points belonging to each group. We'll have a simple little prediction function where if we input a test data set, we'll be given as output the cluster it belongs to. And because KMeans is an iterative algorithm, we'll have this simple run function that is going to run through a bunch of sequences of these steps. And finally, we'll also just evaluate our algorithm with the output method. So I set up our my KMeans as a class just to kind of keep everything organized and make it simpler to call all the functions. So in this initialization, what we have is we're passing the data. This is our data set of values. We're also passing through the k value, and this is just a simple number and represents the number of centroids or the number of clusters that we want to use to assign. We have two other parameters here that are pretty important as well. The first one is broadcasting. Don't worry too much about it now, but I'll basically go over it a little bit later. And the second is verbose. Verbose is simply for debugging. If we have it true, we're going to print out a bunch of kind of debugging information that could make it helpful for you. But as default, I'm just going to leave it as false, meaning we're not going to have this debugging because there are a lot of printout statements. So here we assign our class values that we take in as arguments. And here we assign several other class values that will be important to us. This self.d is simply the dimensionality of the data. Self.centroids is going to be a matrix or a list of lists that holds the centers of these centroids. So the average values of these features of each group. We'll also have a very large list called centroid assignment. And what this list is going to contain is the centroid or the group that every data point belongs to. So let's say we have 3 clusters or 3 groups. Then the possible values will be 0, 1, and 2. So if a data point belongs to group 0, it's going to have a 0 for its index. If it belongs to group 1, it'll have a 1. And if it belongs to group 2, it'll have a 2. So next we have two functions that I just kind of call them utility functions because they're used in the KMeans algorithm, and these can be modified depending on what kind of distances you're using or what kind of loss metric you're using. So in this compute distance function, we're simply taking the distance from every data point to every centroid, and these are denoted as a list A and a list B. So here you can see that we have two cases, one where we use broadcasting and one where we do not use broadcasting. So this is the first little step in this algorithm where broadcasting plays an important role. If you don't know what broadcasting is, You can basically think of broadcasting as a special way that NumPy treats arrays. So the way it does this is that it's able to vectorize computations, essentially so that these computations can be performed in C rather than in Python. It makes the memory allocation much more efficient, and therefore all of your computations are just run much quicker. It's kind of a quick overview of how broadcasting works. The formatting may be a little bit tricky to understand, but you can essentially look at it as how can we take multiple computational steps and just toss it into one line. So for this compute distance, we have a broadcasting statement right here and its equivalent statement in the bottom. I'll explain this statement just so it makes a little more sense. So basically what we're going to do is we're going to look through every element in this matrix A. So these are our data points, for instance. And we're going to look at all of the elements in this matrix B. And these will be our centroids. And what we're going to do is simply take the difference between our value in A and our value in B. So what this is doing is computing the distance from A to B. And we're going to do this for all possible pairs. And this will return a distance list representing the distance from every data point to every centroid. Next, we have this compute loss function. And the loss metric we're using is simply Euclidean distance, meaning we're going to take the distance from a data point and subtract the distance from a centroid and square this so that we can remove negative distances. So using the same kind of notation, we've got the data point, the ith data point, and we've got this little notation that may seem a little tricky at first, but it's really quite simple. So if you can recall, this centroid assignment is basically an indication of for data point I, which centroid do I belong to? That's what the centroid assignment value holds. So if our data point belongs to group 0, it's going to return a 0. And then by indexing into self.centroids, we can get the feature values of that centroid 0. So by taking the difference between the data point and the centroids, we get the distance of the two, and then we square it so that we remove the negative distances. And then we simply take the sum of this loss. So those are the two utility functions that KMeans uses. Now for the actual initialization, what we're going to do is use numpy.random.choice and select k random indices in our dataset. And using these random indices, we'll then select some data points. So if we have k equal to 3, we'll select 3 random data points as our initial cluster centers. Here we have one of the update steps. This is update centroid assignment. What we're going to first do is compute the distance from our data points to our centroids. So we're going to get all possible combinations using our utility function. Now we're going to use a neat little trick that NumPy has, which is this argmin function. If you're not familiar with argmin, basically what it does is it's going to find the value in a list that's the minimum value and simply return the index. So for instance, if we have this little quick example, we have a list that contains the values 3, 5, and 6. If we do numpy.min, well, the minimum value is a 3. However, that 3 doesn't really mean much in terms of assigning centroids. That's why we use numpy.argmin, because for the same list, it's going to return 0, meaning that cluster 0 is the minimum distance. So this is how we assign the centroids for every single data point. Once we have this assignment, then we need to update the centroids. We need to move them around so that they adjust accordingly to the new group that they're a part of. The way we do this is simply grab all of the data points that are part of a specific cluster, cluster K, and then we just take the average of all of these features. So numpy.where is a perfect function for this. And basically how it works is it evaluates a Boolean expression to determine where it should index some other function. So we've got this expression here, centroid assignment equals the k. And we're iterating through k from 0 to capital K. So if we want to have all the data points that belong to a centroid 0, then that means that centroid assignment, when it's equal to k, it's only going to be true if the centroid assignment values are 0, meaning we have all the data points that belong to 0. We have their indices. That's what numpy.where does. Then, if we index into data, we get the actual values of these data points that are part of cluster 0. And then we simply take the average. And that's how we get our new centroid values. Here we have a predict function, which basically does the same thing as the centroid assignment, in that we compute the distance from a test data point to all of the centroids and simply take the argmin, meaning we find the cluster where the distance is the smallest. This last function here is our run function, and because KMeans is an iterative algorithm, we need to run through several steps many times until we reach a final state. First, we initialize our centroids by selecting k random data points. Then we update our centroid assignment, we update our centroids, and we compute our loss. So that serves as the iterative process of KMeans. But how do we actually stop? Well, there's two conditions. We can stop once we've reached the max allocated iterations. In this case, I've simply just put in 100. Or we can be a little smarter about this and look at the loss of our function. So if the loss is not changing, then that means that our centroids have reached their final value and we can stop the algorithm. The way we determine this is by taking the difference between our current loss and our previous loss. And if this difference is very, very small, then we can assume that it's not going to be changing much more. It's kind of reached its asymptotic state. Then we can break our for loop. So that is basically the functionality of the my KMeans class. Now let's use it on a test dataset and see how it works. So here I'm going to load in this iris dataset, just a simple test dataset. And we can see that it has 3 classes. Once this loads, it has 3 classes, 150 samples, and 4 features. And in this cell right here is where we actually call KMeans to run our elbow method to see which k value is the best. There are 2 terms up here that will determine the functionality and how exactly KMeans is run. First we have verbose, which is just debugging, just going to keep that off for now. And here we have broadcasting. So initially I'm going to turn broadcasting to true to see how quickly KMeans runs using broadcasting. And we'll run through the values of k from 1 to 10. And there's this neat little thing right here called the number of restarts. So one thing to note about KMeans is that it does not have a global solution, meaning that every time we run KMeans, we may get a slightly different result. So in order to kind of prevent us from getting a bad result, we essentially run KMeans several times for each k value and take our best centroids, meaning we take the centroids where the loss is a minimum. So in this case, we're going to run each k value 3 times. So running this cell, we'll see some of our output here, and also the importance of this number of restarts, of 3. If we look at k equals 7, we can see that restart 1 had a loss of 40, restart 2 had a loss of 35, and restart 3 had a whopping loss of 681. If we were slightly unlucky with this k equal to 7 and we ran it and we got this loss of 681, then we would get an unfair representation of how k equals 7 does for this algorithm. So by running the restarts 3 times, we can instead select this loss of 35 and get a better feel of where these centroid positions are. Another thing to note is that this took 0.4851 seconds, which is very quick. That will be important in just a moment. And here we can run the elbow method and see that a k value of roughly 2 or 3 is pretty good. In hindsight, since we know that the dataset belongs or contains 3 classes, logically we can just choose k equal to 3. Now I'm going to run this setup one more time, but instead of using broadcasting, I'm going to turn this off. And what this is going to do is use the time-consuming for loop method, and we'll see the difference. So you can notice that it's already taking quite a bit longer to finish everything. So once it's complete, we see that it's roughly 4.5 seconds. And the result is still the same. So there's no loss in accuracy, it simply takes longer. And running this little setup, we can see that for this setup and for this data set, that broadcasting was roughly 9 times faster than non-broadcasting. So even though broadcasting may be a slight mystery to you right now, it's just really important to know that it's a super powerful tool or a super powerful way of implementing code. And it will only become more apparent as your data set increases in terms of number of samples and also in the number of features. Now let's use our KMeans algorithm on a pretty neat example. So instead of using a kind of typical data set, we're going to use images instead. So here I am basically going to load this image, this park image, and run our myKMeans using a k value of 3. So instead of using a kind of typical data set that usually has n samples and d dimensions, we have an image. Well, an image is typically kind of a 3D matrix. It has a height, width, and a depth. The way we can accommodate this is use a reshape function that NumPy has. That will basically flatten the image so that instead of n samples, we have height times width samples. And for the number of features, we'll have 3 because we have a red, green, and blue pixel. So running this KMeans algorithm will, with a k value of 3, will group our pixels or our colors into 3 different groups. So let me run this. It'll take about a minute or so to run it because this is a much larger data set, essentially, than the iris data set. So I'll be right back when this is complete. Alright, welcome back. So here we have our example park image. And we can see that it's got a nice bluish gray sky, it's got some grass and some trees. So after running our KMeans with k equal to 3, we'll see 3 distinct colors, meaning we have 3 centroids and each of them has a R, G, and B value. So opening this up, we have our clustered image. So it's pretty cool. It seems like kind of compressed the colors in our image. We can see that one of the really pronounced colors is this sky because we have a lot of these grayish, bluish pixels. So that's one prominent cluster. And looking in this scene, we have this light green and we also have a slightly darker green. So these are the 3 clusters of our KMeans, and all of the other pixel values have been replaced with these clusters. So definitely check out this notebook and mess around with the value of k and load in different images, and you'll see that with a larger k value, you'll get more values or more colors, but it'll also take a little bit longer to load to run KMeans. That wraps up part 2 of my KMeans Explained mini-series. In this video, we went over the functions that are required to implement KMeans and actually went into the inner workings and the code of the KMeans algorithm. And hopefully you saw a little bit of how it works and the steps that are involved. We also saw a cool example looking at images and how we can apply KMeans on these images to cluster pixels based on their values and get similar regions of color. If you found this notebook useful in understanding KMeans, definitely go ahead and star my Time to Fly Drone and AI Tutorials repository to stay up to date with more code examples for future videos. Also, definitely subscribe to my YouTube channel for more amazing tutorials and content. If you have questions regarding KMeans or any suggestions for this video or future videos, maybe future algorithms you want to see for in tutorials, definitely drop those in the comments below. Otherwise, see you in the next video, and thanks for watching.